Hello, everybody. Peter Devine back again, and today I'm going to run through deriving an equation by which we hope to eventually measure the density of the air by really focusing on the barometric pressure of two locations, one at ground level, the other at a certain elevation, and using a particular formula to kind of ferret out the density of air. We're actually going to use some data collected in 1889 from the then newly constructed Eiffel Tower, which had weather stations both at the base of the tower and at a particular height, about, I believe, 279 feet above. I better get that right, but at some distance above ground level. So as we're looking at this illustration that I've made here, this is what we call a free body diagram of a little slice of air up here, which is an elevation h above ground level. And the upper slice of the air we say is at dh, h plus this small piece dh above ground level. So the air pressure is less up on that upper slice than it is on the lower slice because the air pressure continually gets less and less as we go upward. So we do this free body diagram in a sense. We have the pressure from on the bottom of this slice at height h, the pressure pushing down on this little slice at the elevation h plus dh, and then we also have the weight of the slice itself, which is the density of air times the volume of this little segment here of this slice, which is dh times the area of the base of this little segment. So that's dh times a, and we'll get the mass of that segment then, and we simply multiply it by the gravitational acceleration to give us the weight. So all of these forces act in such a way that this little segment just kind of sits there. It's not blowing around or anything. And any of the forces on the side balance each other, so we don't really have to consider them. So we have two equations from the statics situation here. Statics meaning some of the forces on that little piece of air there is zero. Our first equation is written as in the following way. We'll take upwards as a positive direction and downward as a negative direction. So the area of this kind of tubular piece of air, the base, I should say, the base area is A. If we multiply that by the pressure, we get the actual force pushing up on that. And then we simply take away the force moving down on the upper side of that segment due to the air pressure. So that's the area times P plus dP, where dP is the change in pressure and going from H to H plus dH. And we put a minus sign there because it's acting downward. And then we also have the weight of the segment, which is rho times A times dH, that's the volume. Rho is the density. That gives us the mass times G, will give us the weight of that. And we put a minus sign because it's acting downward. It's all equal to zero. Ultimately, we simplify this and we get dP dH is equal to minus rho times G. That's all well and good. Actually, the density does change with elevation, but problem is that's not going to help us solve what we're looking for. We need to put the density in terms of something we can work with. and we use Boyle's law to do that. You have the equation rho is equal to Kp, that is, the density is proportional to the pressure. The greater the pressure, the greater the density of air. And there's a proportionality constant, which we call K. So in this case, what we do is we put specific values in this formula. Now, let rho sub 0 be the density of the air at ground level. Let P sub 0 be the pressure at ground level. So we can say rho sub 0 is equal to K times P sub 0. And we can solve for K. K is equal to rho sub 0 over P sub 0. And then put it in our formula. So finally we have rho is equal to rho sub 0 over P sub 0 times P. We've replaced K by these two measured values. So finally, now when we see this, now we, instead of rho in this formula up here, we can say P sub 0 over, sorry, we can say rho sub 0 over P sub 0 times P. So replacing rho, we now have dP dH is equal to minus rho sub 0 over P sub 0 times G times the pressure. The variables in this equation are the pressure and the height upon which the pressure is dependent. This is a differential equation, very easy to solve, a very simple one. I'm not going to go into how it's solved, but it's a piece of cake for anyone who's done anything in the calculus, even if they haven't done differential equations. Automatically, this tells us that our solution to this differential equation, which is an equation itself, is as follows. P is equal to some constant times E, which is a particular mathematical constant, which is about 2.78. So that's E to the minus rho sub 0 over P sub 0 G times H, which is our variable. So this is a kind of expression that's going to vary with H in a particular way to give us the pressure. We only need to evaluate this constant. If we look at the ground level situation where H is 0, we just get E to the 0 here, which is 1, so we get, and this is at ground level, so therefore P is P sub 0. P sub 0 therefore is equal to C, and we put that in our final equation. P is equal to P sub 0 E to the minus rho sub 0 over P sub 0 G H. If we solve this equation, if we want to solve this equation for density, which is what we finally want to get, what we do is we take the log, we divide both sides by P sub 0, so we get an expression like this. And we take the log of both sides, we end up getting the log of P over P sub 0 equal to minus rho sub 0 over P sub 0 GH. I'm sorry, folks. I didn't show you any of this stuff up here. I've been blabbing and not showing you what's going on down here. This is our final formula. P is equal to P sub 0 e to the minus rho sub 0 over P sub 0 GH. And if we take the log of divide both sides by P sub 0, and we take the log of both sides, we have the natural log of P over P sub 0 is equal to minus rho sub 0 over P sub 0 GH. And this we can solve quite easily. And what we're going to do is we're going to talk about an H sub 1, which is basically, I mentioned the Eiffel Tower. H sub 1 is simply the height of the weather station at the top of the Eiffel Tower. And so I'm going to put those values in for the last expression that we derived and solve for this little rho sub 0 down here, which was right here. And we end up getting rho sub 0 is equal to, minus P sub 0, it's a little bit fuzzy, minus P sub 0 divided by G divided by H sub 1, log of P1 over P sub 0. P1 being up here at the top of the tower, P sub 0, rho sub 0 being down here. We're trying to solve for this, so it means we have to measure the height of the Eiffel Tower, the pressure at the base, the height, the pressure at the base, which would be P sub 0, and the pressure P sub 1 at the top. And this formula will yield a number which will finally give us the density. Now all we need to do, and I'll do this in a subsequent video, all we need to do is to get those values experimentally, and we are going to be able to do that. So our next video will show how we put the values in and evaluate the density of the air at the base of the Eiffel Tower.